So, in the last class we said that the next step in our analysis would be to take into account irreversibilities and losses associated with irreversibilities in our analysis. So, what we have sketched here is the basic turbojet cycle. In the earlier version of this cycle, all the processes were ideal. So, we went from A to 0 1 along a vertical line like this, and from 0 1 to 0 2 along a vertical line, and then there was a constant pressure heat addition process and so on. Now, you can see what irreversibilities do to the process and the state points. So, you can see that there is an increase in entropy in going from A to state 0 1, and so consequently the state point 0 1 shifts to the right. And once again, when we go from stagnation state 0 1 to 0 2, again due to irreversibilities, we can see that there is a shift to the right, and this is going to cause, there is going to be a loss of stagnation pressure associated with this. Although this is a compressor and we are putting in work to increase the stagnation pressure, as a result of the irreversibility, some of the work that we put in is definitely going to be lost. Okay. And then in going from 02 to 03, we can see that the heat addition process also results in loss of stagnation pressure, and also there is a loss of static pressure, as you can see from here. Okay. So, this is due to the mixing, which is an irreversible process, and other chemical reactions and other things. So, there are definitely going to be losses associated with this. And 03 to 04 is the expansion process in the turbine, which once again, because of irreversibilities, you can see that the state point shifts to the right, and whatever work it could have produced, right, if it is had the expansion been isentropic, we would have just gone down here. So, whatever work we could have obtained from the turbine is now going to be, whatever we are getting now is going to be less than whatever we could have obtained earlier. Right. So, because of the irreversibility, then here you see expansion in the nozzle, and similar to what we discussed for the other components, the expansion process for example will give only slightly less velocity than what we would have obtained had the process been isentropic. Okay. So, what we need to do now is come up with a way to include the effects of these irreversibilities in our calculation. So, for example, when the state changes from A to 0 1, 0 1 to 0 2 and so on, we need to have a way by which we can take this into account. So, we are not going to actually try to evaluate the amount of losses due to these irreversibilities, because that is not a measurable quantity. Okay. You know only from experience that there is so much loss of pressure. So, we do not know exactly what the mechanisms are which cause that loss of pressure. So, what we will do is we will define an appropriate efficiency for each one of this process, and then assume the process to be less efficient than the ideal process. So, if the process is ideal, the efficiency is 100%, and that would be an isentropic process. So, what we would say is the process is non-ideal. So, let us say the efficiency is only 90%, then how do we calculate the downstream states if the efficiency were 90%? So, that is the way in which we will proceed. We will not try to justify why the efficiency is 90% or why it is 95%. That is a value that we can take from practice, that it appears to be 90% efficient. We will accept it as it is without asking any questions about how it became 90%. So, we start, so what we are going to do now is we will take each leg of this simple cycle and define an efficiency, and then see how the downstream states can be calculated based on this. So, the basic idea is to keep track of this stagnation state 0 1, 0 2, 0 3, 0 4, and then this static state E at the exit. That is the basic idea. Okay. And this is the free stream state A. So, let us start with the first component, which is the inlet. Okay. So, the inlet, as you can see, has a static state corresponding to this. So, this is the inlet, this is the free stream stagnation, I am sorry, this is the free stream static temperature, and this is the free stream static pressure, and this is the inlet state. So, the flow approaches the engine at this static state. This is a static state. Okay. Now, the corresponding stagnation state for this can be depicted like this. So, this is 0A, that is the stagnation state corresponding to the free stream static state, and you can see that the stagnation temperature is T0 and the stagnation pressure is P0A. Okay, starting from this static state, the flow is going to be decelerated at the inlet, and there is going to be an increase in static pressure, right? That is what we are looking at. So you can see that starting from this static state, the flow undergoes a deceleration process, so that there is an increase in static pressure, right? Notice that the velocity component, which was equal to this, so this is nothing but VA square over 2 Cp. Okay, starting from there, now you can see that the velocity has reduced. Remember, stagnation temperature remains the same because there is no work or heat interaction in the inlet. So stagnation temperature remains the same. So you can see that static pressure has increased, but VA square or V square over 2 Cp has reduced in magnitude. And so we go from here to here, and I have sketched this using a dashed line to illustrate that there are irreversibilities associated with the process. And you can see that this is the stagnation state 0,1. This is the stagnation state 0,1, this is P01. Notice that T01 is equal to T0A because there is no heat or work interaction during the process. One performance metric for evaluating this particular component, which is the intake, is to use the stagnation pressure recovery. P01 over P0A is a suitable metric, right? So there is a loss of stagnation pressure because of the irreversibility, as you can see from here. The stagnation pressure line shifts from this, which is P0A, to this. So the state point stagnation state moves to the right, and that moving to the right is a result of this process moving to the right. So due to increased entropy and irreversibility, so P01 over P0A will be equal to 1 if the compression process were isentropic, otherwise it is something less than 1. So this is a metric which is used routinely and it can be used. There is also a slightly different metric which is used for subsonic inlets. This is a metric that is typically used for supersonic intakes, and for subsonic intakes there is a metric which is used which goes like this. The idea is, we know that the stagnation state changes from P0A to P01, right? The stagnation temperature remains the same, so the stagnation state goes from here to here. So we are willing to concede that this change in stagnation state is inevitable, it is always going to happen. But what we try to say is the following: had this change in stagnation state taken place as a result of an isentropic process, what would the stagnation temperature have been? Okay, so you need to listen to this carefully. Remember, the stagnation state here goes from here to here because the stagnation temperature remains constant in the actual device. What we are going to do is come up with the definition for the efficiency of the device by arguing like this: what if we say that we go from a P0A to P01 in an isentropic process? If we had done that, what would the change in stagnation temperature be? Right? So this is what the stagnation state would have come to. Remember, this is along the same isobar, right? So the P01S is equal to P01. The stagnation pressure here is the same as this state, but notice that because we are constraining it to be isentropic, it has to lie along this vertical line and not along this horizontal line, which means that the stagnation temperature is this. Since in our steady flow energy equation, we have the stagnation temperature appearing in our steady flow energy equation, we try to relate the efficiency of the devices to changes in stagnation temperature, because that we can relate to either heat or work interaction. Right? Our energy equation does not have stagnation pressure, it has only stagnation temperature. So that is the rationale for relating these two changes in stagnation temperature. Okay? The corresponding static state would have been equal to this. So in the actual inlet, we go from this static state to this static state, and due to the irreversibilities, there is a loss of stagnation pressure from here to here. But because there is no heat or work interaction, stagnation temperature remains the same. That is the scenario in the actual intake. Now, in order to quantify this, we are proposing a metric which states the following: had the compression process been isentropic, what would the stagnation temperature be at the end of such a compression process while the stagnation pressure is equal to P01? Okay, yes?
1S signify?
1S is the static state at the end of such an isentropic compression process.
It is not equal to P1.
That is not equal to P1. What we are saying is 1s is the static state which would correspond to a stagnation state 0 1s. So we are coming back from the 0 1s state. We are saying P0 1s is such that is equal to P0 1s is equal to P0 1. Corresponding static state would have been this. Okay. So the efficiency can be defined like this. For subsonic inlets, it is better to define the efficiency this way. So we say that the efficiency is T0 1s minus Ta divided by T0A or T01 minus Ta. Yeah, go ahead.
So why there is loss of stagnation pressure if we are assuming it to be this one isentropic process?
No.
Why there is loss this one stagnation?
Yes, I am assuming it to be an isentropic process only until I reach stagnation pressure P01s. I am not assuming it is an isentropic process all the way. If I do that, then the efficiency is 100%. Remember, there is a loss of stagnation pressure. Correct? In the actual intake, there is a loss of stagnation pressure. We go from P0A T0A to P01 T01 with T01 being equal to T0A. What I am going to do is I am going to convert this into an equivalent changes in stagnation temperature. Okay? So we go from P0A T0A to P01s and T01s, okay, along an isentropic path. So if you look at this diagram, we can see that we go from 0A to 01s, and 01s is such that P01s is equal to P01. Okay, and so the efficiency is defined like this. Notice that if the entire process, if state 1 were to be over here, then this will have 100% efficiency, otherwise we have a certain value for the efficiency. Okay. So this is used for subsonic inlets only. For supersonic inlet, we will use either this or a slightly different metric. Okay. So we will take a look at supersonic inlets when we go to ramjet engines. For now, we will use this definition for this. Okay. So we now go to the next component, which is the compressor or the fan. Both can be handled in the same framework. So we look at the compressor, and so as you can see from here we go from static state 1, which is at the end of the inlet and at entry to the compressor. The static temperature is T1, static pressure is P1 here. So we go from there. The corresponding stagnation state is 0 1. So you can see that T01 and P01 are like this. Now in the compressor, we are going to add work such that the pressure ratio becomes, let us say, 20, 30 or 40. So we are adding work in the compressor, right. So there is going to be a change in stagnation pressure, right. But how much of this change in stagnation pressure is due to an increase, is due to an input of work, and how much is the loss due to irreversibility? That is what we need to look at, right. So the compression process takes the static state from 1 to 2 like this, right, and because we have put in work, the stagnation pressure corresponding to this state will be higher than P01, right. So this is stagnation state 02, right, and it is going to be higher than P01. So P02 over P01 is going to be equal to the pressure ratio across the compressor, 20, 30 or 40, whatever we specify for the particular engine. Now we are going to quantify the efficiency of this device in the same manner as we did before. So you can clearly see that the stagnation state changes from 01 to 02. Right. We want to relate this change to we want to make sure that we can relate this change to a change in stagnation temperature for an isentropic process. So what we are going to say is, if the stagnation pressure changes from P01 to P02 in an isentropic process, what would the stagnation temperature have been, right? That is what we are going to see. So if you look at this, as I said earlier, compressor pressure ratio is P02 over P01, that will be 20, 30 or 40, and so you can see that this is the stagnation state that we are looking for. Had the increase in P01, had the increase in stagnation pressure from P01 to P02, had it taken place in an isentropic manner, this would have been my end state, T02s. right, then you can see that the amount of work that I am putting in, which is related to the change in the stagnation temperature, T02S minus T01, as you can see, is less than T02 minus T01, right, which means in the actual process, due to irreversibilities, I have put in more work. To accomplish the same change in stagnation pressure, I am now putting in more work. That is what this definition allows me to do, right. So, T02S minus T01 is the work that I would have put in an isentropic process for the same pressure ratio. Instead of that, I am now putting in T02 minus T01 in the actual compressor to accomplish the same pressure ratio. So, the efficiency of the compressor can be defined like this: T02S minus T01 divided by T02 minus T01. Notice that I have kept the pressure ratio the same, P02S is equal to P02. So, that the pressure ratio for this isentropic process is the same as the pressure ratio for this irreversible process. Go ahead.
In the inlet, there was no work addition.
There was no work addition.
Here, but there is work addition. So, why we are going for the same kind of definition for this case also? Because there was no energy transfer.
Correct.
But here, there is a transfer. So
but there was a change in stagnation pressure there due to irreversibilities. Correct. So, we are trying to convert that into a change in stagnation temperature. Remember what we said in the first lecture when we talked about stagnation pressure. Any loss of stagnation pressure is tantamount to a loss of work, correct, which is why I am relating changes in stagnation pressure to changes in stagnation temperature, because our energy equation, if you remember, our energy equation contains T plus U square over 2 Cp, which is the stagnation temperature. So, now right hand side can contain W dot, which will be a rate at which I am adding work. So, any change in stagnation temperature I am able to relate to either a heat input or a work input, which is why changes in stagnation pressure are being related to changes in stagnation temperature. In the previous case, there was no work or heat interaction, so there was no change in stagnation temperature, but there was a loss of stagnation pressure, which I translated to a change in stagnation temperature to illustrate the fact that is loss of work, equivalent to a loss of work. Here I am actually putting in work, and for the amount of work that I am putting in, I am able to increase the stagnation pressure from P01 to P02. If this process had been isentropic, I could have realized the same change in stagnation pressure with a less amount of work, as you can see from here. Okay, I am sorry, as you can see from the difference between these two. So, that is why we are relating everything to an equivalent change in stagnation temperature. Okay, right. So, you can see that this is the efficiency that we are going to use for the compressor. Combustor, since we are not looking too much into the actual heat release mechanism or the process in the combustor, and we are not interested in doing that also, because as we showed earlier, the processes in the combustor are essentially incompressible. So, we are not worried too much about it. What we will do is define two metrics for the combustor performance. One is the loss of stagnation pressure. Okay. So, I go into the combustor with a certain stagnation pressure, as we saw, let us say P02. How much am I losing in the combustor as a result of mixing and combustion and so on. So, I will specify, usually a percentage is specified. We may say that there is a 10% loss of stagnation pressure in the combustor, and so when we come out of the combustor, we will say at the exit of the combustor the pressure is 0.9 times the pressure at the inlet. So, I know the stagnation pressure at the exit, and now if I also think about the combustor itself, it is quite possible that I put in a certain amount of fuel into the combustor. So, I know that based on the calorific value of the fuel, there should be a certain change in stagnation temperature, right? There should be a certain release of heat. But in the actual combustor, a lot of the energy goes towards heating the various combustor parts and so on. And we are also cooling, so there are many heat losses in the combustor. So, I may put in 1 kg of fuel and burn 1 kg of fuel in the combustor, but I may not be able to realize the calorific value contained in 1 kg of fuel as an increase in the stagnation temperature of the fluid, right. So, I define my combustor efficiency that way. I say that what is the amount of fuel that I need to put in for realizing a certain change in stagnation temperature, that is the ideal fuel air ratio. So I know that my turbine entry temperature cannot be above this value. So I calculate, so given my inlet condition to the combustor and my exit temperature, what is the amount of fuel that I need to burn to go from here to there under ideal circumstances. And under real circumstances I need to put in more because I am losing some of the heat to heating of the components, to cooling and so on. So the actual value will be more. So that I define to be my combustion efficiency. We will assume some typical values for combustion efficiency. 90% is typically a good value, which means that if I want to realize a certain change in stagnation temperature, I need to put in more than the ideal amount of fuel to realize that change in stagnation temperature. Okay, and that is how we are going to characterize the operation of the combustor. We do not want to get into details beyond that. Yes.
So in combustor, the stagnation pressure is changing because of two parameters. One is heat is added, and the other is reversibility.
Correct. Correct.
Then we are considering both of them.
This 10% loss is inclusive of both. That is obtained from practice. We can actually take both these effects into account. Remember, the flow in the combustor is almost on the incompressible limit. Okay, so the loss of stagnation pressure due to heat addition, which is typically something that you would see in a compressible flow, will be largely absent in the actual combustor. The loss of stagnation pressure that you see in the combustor is due to mixing. It's a lot of mixing, so that is what causes the loss. So the loss of stagnation pressure due to heat addition will be somewhat minimal in this case due to reduced compressibility effects. Okay, so this 10% should be more than able to include all the other things, and these are numbers, as I said, these are numbers derived from practical situations. Typically in these combustors, what would you see? So that is what is used here. Okay, without going into the details of how this value came about. Next component that we are going to look at is the turbine, and TS diagram of the process in the turbine looks like this. So we start from static state 3, which is at a pressure P3, and the corresponding stagnation state is 03 with stagnation temperature T03 and stagnation pressure P03. So now we have an expansion process, as you can see. The expansion process shifts to the right. So the downstream state from the turbine is over here at a higher entropy, and this is the static pressure P4. Now corresponding stagnation state is 04 with stagnation temperature 04 and stagnation pressure 04, P04. So what has happened in this process is that the stagnation pressure has decreased from P03 to P04, which means some amount of work has been taken out. Remember, decrease of stagnation pressure can be due to work extraction or irreversibility. So what we are trying to quantify now is how much of this is work extraction, how much of this is irreversibility. And we quantify that by saying, if the same change in stagnation pressure had it taken place isentropically, what would have been the change in stagnation temperature, which would then tell me how much work I would have obtained. Right? So if I do that, the corresponding static state would have been 4s, and the corresponding stagnation state would be 04s. So you can see that if the process had been isentropic, then the amount of work that I would have obtained would be T03 minus T04s, which is more than what I am getting now, which is T03 minus T04. Okay. So this nicely quantifies the loss due to the irreversibility. That is the usefulness of this particular calculation. Remember, all these other components, the compressibility effect is important. Except for the combustor, we showed in our first lecture that compressibility effect is important in all the other components, which is why we are dealing with stagnation quantities rather than static quantities in all these definitions. Okay. Your probably first or second year thermodynamics course would have probably defined these efficiencies using static states rather than stagnation states. It is okay for a basic thermodynamics course, but we are doing a propulsion course. So we need to make sure that the numbers and the models that we use are as realistic as possible. Okay. So the efficiency can now be defined as T03 minus T04 which is the lesser amount of work that I am getting now compared to T03 minus T04S. So, the common thread in all these definitions of efficiency is that there is a change in the stagnation state, right. What if the change in the stagnation pressure had been achieved using an isentropic process? Then what would have been the change in the stagnation temperature? So, and we can relate that to work or work. Basically, we are not worried about heat, so we are talking about work in all these cases. We can relate that to work through our energy equation. So, there is a common thread in all these definitions. The last component is the nozzle, and again the process in the nozzle looks like this. So, we start from state 4, which is at static pressure P4, and the corresponding stagnation state is 04, T04 and P04, and the expansion takes place from 4 to an exit state E to a static pressure PE. Remember, in the nozzle what we need to think about is the exit static pressure, because the thrust is determined by the exit static pressure, which in turn determines the velocity as well as the pressure thrust. Okay, so that is what we must think about in this case. Remember, in the inlet also we use the static quantities A, and then we related that to the stagnation quantity. So, in the nozzle also we do the same thing. In the compressor and the turbine we relate stagnation quantities at inlet and at exit. Okay, whereas for the inlet and the nozzle we relate the stagnation quantities to the appropriate static quantity either at the inlet or at the exit. In this case it is at the exit. Okay. Now, as a result of this, what is the stagnation state corresponding to E? That is T0E with the stagnation pressure of P0E. Notice that this is equal to VE square over 2 CPG, where this additional subscript G denotes the fact that we are dealing with combustion gases and not air. So, the Cp for that is going to be different from Cp for air. We need to take that into account. Cp for this will be higher actually at a higher temperature. Although we are strictly speaking not abandoning the calorically perfect assumption, but this is still something that we can easily, we are assuming the Cp to be constant for this entire gas downstream of the combustor. So, downstream of the combustor we assume a different value for Cp, different value for gamma. Upstream of the combustor we assume the value is same as that of air. That is something that we can easily accommodate, it is not a problem, and the results will be more realistic. Okay. So, now what are we going to do? We can see that there is a change in stagnation pressure from P04 to P0E. Had this change taken place isentropically, what would the exit velocity from the nozzle would have been? What would the exit velocity from the nozzle have been, right? So, the exit state, remember we want to go to the exit state ES because we are going to expand against the same pressure, exit pressure. So, the corresponding state would have been this. Okay. The change in stagnation pressure here is accommodated in this device using by comparing these two velocities. Okay. Notice that in this case we are not going to go down here and say that had the process been isentropic, what would the velocity have been. What we are saying is if I expand from this stagnation state to this static pressure, remember the static pressure has to be the same in both cases for the comparison to be fair for this device. So, we are saying this is my VES square over 2 CPG, this is the velocity that I would have obtained if I had expanded isentropically to this static pressure. Okay. In the real case this is the velocity that I am getting. Okay. So, the efficiency of the nozzle can be defined like this. T04 minus TE divided by T04 minus TES, because the conversion of the enthalpy to kinetic energy is what we are trying to do in this particular device. Okay. Similarly, if you look at the efficiency expression for the inlet, you would notice that you get a similar kind of thing, velocity square at the exit of the inlet divided by velocity square at the free stream, right, because the inlet is also supposed to recover the momentum of the fluid as pressure. That is why that efficiency is defined in that way. This is also defined in the same way because of the objective that we are trying to accomplish in this device. So, the efficiency metric should take that into account. What are we trying to accomplish with this device? Right? If it is a work addition or work extraction device, then we need to track the changes in stagnation pressure. If it is a device where we are trying to convert momentum into enthalpy or enthalpy into momentum of the fluid, then we need to make sure that the definition of the efficiency reflects that fact. And that is what we have done here. Okay, so this is the way in which we take the irreversibilities and losses into account. When we do the calculation, we will assume certain typical values for all these efficiencies. These are the so called isentropic efficiencies. We will assume certain typical values and do our calculations. Okay. Now, with the nozzle, there is one more complication. Okay, what is the complication? The complication is we have said that this is exit pressure PE. Now, this exit pressure PE is going to be different depending upon whether the nozzle is choked or not. If it is choked, then the exit pressure is equal to the ambient pressure. If it is not choked, then the exit pressure is equal to the critical pressure. M is equal to 1. So, it is equal to the critical pressure. So, how do we evaluate the critical pressure for a nozzle in which there are irreversibilities? So, previously the nozzle process was isentropic, now it is irreversible. So, we need to make sure that we know how to do that. How do we evaluate this PE? Right? That is the extra complication with the nozzle. Let us see how we do that. So, we take this situation one at a time. The nozzle is not choked, that is a simple case. Then PES is equal to PE is equal to PA. Remember, the state ES and state E lie on the same isobar. Right? State ES and state E lie on the same isobar. So, PES equal to PE equal to PA. Correct? And so, then I can write the following: PES over P04, both of these states lie on the same isentrope. Correct? ES and 04 lie on the same isentrope. If you see the earlier figure, you can see that very easily. So, I can use this relationship to evaluate my TES. T04 is known, PES is now known, P04 is also known. So, I can evaluate my exit static temperature this way. So, when you want to evaluate the thrust from this engine, what quantities do we require? We are going to show that next, but we have already talked about thrust and other things. There are only two quantities that we need at the exit. Those are velocity and exit static pressure. So, now in this case I know the exit static pressure and I need to calculate the velocity VE, right. So, I can calculate the velocity corresponding to that state, because T04 is equal to TES plus VES square over 2 CPG. So, I can calculate VES square based on this relationship. Once I have this, I can calculate the exit velocity using the definition of the nozzle efficiency. Okay, so, now I have both the quantities that I wanted, the exit pressure, exit static pressure and the exit velocity. This is for the case when the nozzle is not choked. Okay. If the nozzle is choked, then the exit velocity we know is equal to the speed of sound, right. So, VE square is equal to gamma RT, right. And if I write this in terms of my stagnation temperature, remember the stagnation temperature does not change in the nozzle, only the stagnation pressure decreases due to irreversibilities. Stagnation temperature does not change. So, I can rewrite this in terms of that, and after using the fact that Mach number is equal to 1, right. So, I can write it like this. Correct? T04 over TE is equal to gamma G plus 1 over 2, because the Mach number is equal to 1 at this point. So, I can write it like this. So, I have this relationship. So, once I have this, I can calculate VES square from the definition of the nozzle efficiency. So, which makes this expression look like this. So, I get this expression for VES square. Remember from our earlier figure, VES square is always greater than VE square. Okay. So, this definition has a slight theoretical difficulty which we must actually overlook, because we have no choice. Remember, In this case, we have said that the nozzle is choked. So, we have used that fact here, the actual nozzle is choked, right. So, this is equal to the speed of sound. Now, I am calculating a VES square which is more than this value, but it is still a convergent nozzle. So, it is theoretically from a gas dynamic perspective, it is not possible to have a speed more than the speed of sound in a convergent nozzle. But remember, this definition does not take gas dynamic aspects into account, it is only a thermodynamic definition. Isentropic efficiency is only a thermodynamic definition. Okay, it assumes that you will do whatever it takes to accomplish this velocity VES square. So, in the theoretical definition we may say, okay, maybe it is a convergent divergent nozzle, but somehow you will accomplish that VES square. Okay. So, that is something that you must keep in mind. To reconcile this with the gas dynamic aspects, what we are saying is this may be a slightly different nozzle where the velocity is VES square, which is slightly more than this. Okay. Because many times when you do the calculation, you realize this and then you are startled. Should this be equal to the speed of sound or should this be equal to the speed of sound? Remember, the actual nozzle is choked. So, correct representation of what you see in practice is to keep this equal to speed of sound. And then assume that in this process, remember, this is an imaginary process, right. This imaginary process I can accomplish in many different ways, starting from the same stagnation and static state, I can make this expand in a CD nozzle such that I accomplish this velocity, keeping other things also the same. That is possible to do. Okay. So, once I know this velocity, I can calculate my static temperature again from the definition of the stagnation temperature, right. TES is T04 minus VES square over 2 CPG. So, this finally gives me TES like this. Remember, what am I looking for? I am looking for two things, exit velocity and exit static pressure. I already have the exit velocity, I am looking for exit static pressure. So, what I am going to do is do the same as what I did in the previous case, relate PES and P04 and TES and T04 using an isentropic relationship, right. So, that is what this does, PES over P04 is equal to TES over T04, right. So, in this relationship I know TES, I know T04, I know P04, so I can evaluate my PES. And remember, state point ES and state point E lie on the same isobar. So, PES equal to PE, which in this case is also equal to the critical pressure. So, this is what the relationship looks like. So, this is the expression for critical pressure in a nozzle where there are irreversibilities. If you set eta nozzle equal to 1, meaning there are no irreversibilities, then you recover the expression that we derived earlier for an isentropic process. So, the only change is this goes inside now. So, at the end of this exercise, now I know VE square and also PE. So, we have to look at two situations. We have to first of all determine whether the nozzle is choked or not. In the actual calculation, what we will do is, given P04, eta nozzle and the other quantities, we will determine the critical pressure. Then compare the critical pressure with the ambient pressure to see whether the nozzle is choked or not. Remember, the flow in the nozzle can only be under expanded, not over expanded, which means the ambient pressure can only be less than the critical pressure, not more than the critical pressure. So, we evaluate this and then determine whether the nozzle is choked or not. Once we make the determination, we can then go through and determine the exit velocity. Alright. So, we will demonstrate this as we go through the calculations. So, that takes care of irreversibilities in each one of the components in the device. So, when we add for example, something like a fan or other turbines, we can use the same definitions to deal with that. Okay. So, we have demonstrated this for a turbojet engine, but the definitions do not change if you use it for a turbofan engine also. Okay. That is what we will do, because the addition of a fan is like a low pressure compressor. Right. So, there is no problem in using this. The fan nozzle is a cold nozzle, again gamma G will be replaced by gamma in a fan nozzle. That is the only change that we are going to see. So, we can use this for a turbofan engine also. The next part that we need to do is develop expressions for thrust. Right. We want to do thrust calculations and thrust specific fuel consumption calculation. So, we start with that. So, we first derive a general thrust equation. Okay. So, we look at an engine. So, this is an engine, right. Air approaches the engine with velocity Va and air leaves the engine with velocity Ve. Okay. So, we are putting in a certain amount of fuel flow rate and the engine produces a certain amount of thrust, which is what is measured or felt by the frame in which the engine is mounted. Okay. So, we label this state, entry state, as A, and we label the exit state as E. So, if you apply impulse function between these two states, I can calculate the thrust, it is not a problem. So, thrust is equal to impulse function at the exit minus impulse function at the inlet, right. So, if I substitute for this, I get the following. So, impulse function is nothing but P plus rho V square times A, right. So, this is the impulse function at the inlet, this is the impulse function at the exit. Remember, the mass flow rate through the engine, if I do not take this into account, m dot f is usually much smaller compared to the air flow rate, we know that much, right. So, mass flow rate at any station is going to be rho times A times V, right. So, the mass flow rate at inlet is going to be rho A times Va times this, and mass flow rate at exit is also rho E times Ve times this. So, if I make use of that, I get the following. I can write this in terms of mass flow rates like this. Okay. Usually the mass flow rate that goes through the engine in this direction, air mass flow rate, is usually of the order of about 500, 600 or even more, 700 or 1000 kilogram per second, whereas the fuel flow rate is of the order of probably few grams per second, kilograms per hour, grams per second approximately. Okay. So, we can easily ignore this and use this expression. Now, you must keep in mind what we said earlier, right. If you remember in our earlier discussion on thrust, and where we said that thrust can also be evaluated by integrating the pressure force on the metal surfaces, and we showed this graphic earlier, we can see that the net force on the metal surface is going to be the internal pressure minus the ambient pressure, which is constant. So, you can see that the ambient pressure vector remains constant here. So, the net force in this is going to be this pressure minus the ambient pressure, and I do this throughout, okay, which means that at every point here I need to measure my actual pressure with respect to the ambient pressure. So, I have to subtract the ambient pressure from this pressure throughout, right, in order to calculate the net force on the metal surface, right. So, we are calculating thrust, which means that this pressure must be measured with respect to the ambient pressure, local ambient pressure. Remember, local ambient pressure keeps changing. When the engine takes off, the ambient pressure is sea level static pressure. When it is cruising at 30,000 feet, it is less than that. So, we subtract the ambient pressure from these two, and if you do that, what do you get? This becomes PE minus PA, and this becomes 0, exactly. So, this term disappears. So, we end up with this equation which is the general thrust equation for a turbojet engine, single stream engine, where we have assumed only one stream here. Okay. So, there is only one stream that enters and leaves. Okay. So, you must be very clear about why this term disappears, and that has to do with the fact that net force on the engine is always the pressure force after subtracting the ambient pressure, that is the net force. Okay. Any questions? What we will do in the next class is develop this expression, look at this expression closely, analyze it, draw some inferences, and then write a similar expression for a turbofan engine also. Remember, turbofan engine has two streams. One is the bypass stream or cold stream, the other one is the core engine stream or hot stream. So, we will develop an expression for the turbofan engine also, and then we will keep everything ready. The next module we will try to do thrust calculations, evaluate the thrust for actual engine using these expressions.